The part 1 mechanical modification. As a part of the mechanical modification, today we'll talk about the compaction. The learning objectives of today's lecture is to understand the purpose of the compaction of soils and to describe the laboratory procedures of the compaction test and to identify the dry density and water content relations such as the compaction curve. So the mechanical modifications are techniques that involve the application of the external forces to improve the engineering properties of the soil, such as by compaction. So it involves the external mechanical forces. And the compaction is the expulsion of air due to the application of the short-term load. So air. We call it short-term load because we are applying the dynamic loads, which result in the closure packing, while the volume of the solid and the water content remains essentially the same. So during the compaction, let's say that we have the particles here in this volume before the compaction, and after the compaction, the volume decreases, right? So the total volume decrease, but the dry mass, so the total mass of the solid inside this volume doesn't change, so it's constant. And the void ratio also decrease, and dry density will increase because the volume is increased. Major aims of this compaction is to increase the shear strength and stiffness and reduce the compressibility and void ratio and reduce the permeability and reduce the liquefaction potential and to control the swelling and the shrinkage of the soil and to prolong the durability, so increase the durability. On the other hand, we sometimes use the consolidation, but consolidation is a totally different process from the compaction. So the consolidation is the expulsion of water instead of air to reduce the volume of soil due to the application of the long-term load. Here, so during the consolidation, we don't change the load that much, so it can be called as a static load, and this results in also the closure packing. And consolidation involves the transfer of the stress from the liquid to the solid grains. And then what is the stabilization? Stabilization is the increase in strength or reduction in deformation of the soil mass by application of the chemical additives, such as the cement, lime powder. So this will involve the physical and chemical modification. So the compaction is defined as the densification of the soil by mechanical energy. This is probably the oldest technique and the most commonly used technique. Historically, the elephants were used in Southeast Asia for the road construction. So it's been very old, but still people use it very popularly. And 1920s, the dams in the United States were built by dumping materials in a loose state, but the failure often occurred. So the 1930s, Ralph Roscoe Proctor, so-called R.R. Proctor, showed that the dry density of a given compactive effort depends on the amount of water in soil. So he basically showed that the compactness and the denseness of the soil after compaction depends on the water content. So he developed a laboratory procedure for the compaction, and it's called the standard Proctor test or the standard compaction test. The purpose of this standard Proctor test is to determine the proper amount of the water to use and the resulting degree of the denseness, so the resulting dry density for this optimum water content when compacting the soil in the field. He also found that the compaction is a function of 4 variables. First is the dry density, and the dry density is a function of the water content, W, and also the compactive effort or the mechanical energy that you apply to this soil. And lastly, also it depends on the soil type, whether it's well graded or poorly graded, or how much fine fractions it contains, or if there's a clay mixed in the soil or not. So we're gonna go over the method of the compaction. This class will talk about the laboratory procedure. Laboratory procedure is to aim at the simulating field compaction procedures and aid in the optimization and control of the placement condition. So basically, we have to decide the optimal water content for the placement field at the field from this laboratory method. The most common tests are the standard proctor test and the modified proctor test. And standard proctor test, both tests employs the dynamic compaction. So we apply the impact force to the soil, top of the soil, while compacting the soil in layers. The details of this method are specified in many specifications like ASTM or AASHTO or the British standard. Basically, it involves the compaction mode, which is the circular type, and you put the soil inside the layer by layer, and for each layer you apply the impact force using this compaction hammer. In the modified compaction test also has been specified in many specifications like ASTM, AASHTO, and the British standard. So if you are interested in that, please look at more details in this manuscript. So when we calculate the specific energy applied or compactive effort, it will depending on several parameters. For example, how much height we drop the hammer. Right? So the height will be one factor, and the weight of hammer is another factor, and also the number of layers during the compaction. So for a given volume, we can tempt the soil in like 10 layers or 5 layers or 2 layers, right? Depending on the layers, you will apply the different energies. Normally, when you compact in the laboratory, you apply the hammers in these kind of sequences. So you apply like each directions, and then you just go circular and to be flat. And specific energy can be calculated using these parameters. The equation that we can use is that the specific energy EC is function of N, the number of blows per layer, and the number of layers, and weight of hammer, and the height of the drop, and divided by the volume of the soil. So this gives you the specific energy that you apply during the compaction. So if you increase the number of layers, then you're applying so energy will proportional to the number of layers, so it's going to increase more. If you apply the number of blows like 25 blows or the 50 blows, as you increase the number of blows, also the specific energy increases. Also height and the weight will be the same, but as you decrease the size of the volume, size of the soil specimen, then you're applying the same amount of energy to the less volume, so specific energy will be also a function of the volume. So when you compare the standard compaction test and the modified compaction test, you can calculate the different specific energies because you use the different hammers and the different conditions. For example, the weight of the hammer in the standard proctor test, it used 5.5 pounds, so it's about 2.5 kilogram. In the modified proctor test, it used 10-pound hammer, so it's about 4.5 kilogram. The volume of the mold are the same, it's about 1,000 cubic centimeter, and the height is 1 feet for the standard proctor test and 18 inches for the modified proctor test. If you convert it to the SI unit, that's going to be 30 centimeter, and it's about 45 centimeter. Number of layers in the standard proctor test, you used 3 layers, and in the modified proctor test you use the 5 layers. But you use the same number of loads, 25. So if you use these parameters to calculate the specific energy using this equation, then you have this value, that specific surface energy you apply for the standard proctor test is about 600 kilojoule per cubic meter, and the modified proctor test is about 2700 kilojoule per cubic meter. So it's more than 2 times, or even I think it's about 4 times larger. Okay. So the basic test procedure for the compaction test is as follows. So you have a moist soil, so the amount of the water is a bit controlled, and you compact the soil in a mold according to the procedure. And after you finish all the compaction, you measure the total density. So rho T is the mass of total mass over the total volume, and also you measure the water content by sample the soils and do the oven drying. So the water content will be the mass of water divided by the solid mass. And you calculate the dry mass. When you calculate the dry mass, you use this equation. So the total mass divided by the 1 plus W will give you the dry mass. So the reason that we are using the dry density is because it's now affected by the water content. So if it rains, the total density will increase, but as long as it keeps the void ratio constant, then dry density will remain the same. So dry density will be one indicator for the denseness of the soil. So repeat for this procedure for several water content. Mostly people do it for 5 to 6 water contents. Then you can plot the chart, dry density versus the water content. So this gives you the compaction curve. So these dots are the test results, and when you connect these dots, then you're gonna get this kind of a compaction curve. And from the compaction curve, you can find out several parameters. One is the maximum dry density. So the peak value of this compaction curve gives you the maximum dry density, and the corresponding water content is defined as the optimum water content. So the x-axis here is the water content. And this side of the water content is called the wet side of optimum. The water content less than the optimum water content is called the dry side. Normally the maximum dry density, the maximum range of the maximum dry density is about 1.3 to 2.5 megagram per cubic meter. Typically, it ranges 1.6 to 2 megagram per cubic meter. And for the optimum water content, it can range from 5 to 40%, but typically it ranges within the range of the 10 to 25%. For the fine grain soil, the optimal water content is slightly less than the plastic limit. But please be aware that this curve does not necessarily reflect the maximum dry density that can be achieved in the field, because the depending on the compactive effort, you get different maximum dry density. So as you use the higher compactive effort, your maximum dry density increases, so that the compaction curve for the standard Proctor test, if standard Proctor test is here, then the modified Proctor test will placed here. So you have a higher maximum dry density and the lower optimal water content. If you increase the compactive effort more, then it's gonna be placed here. So if this is the EC compactive effort 1 and compactive effort 2, and this curve is the compactive effort 3, then compactive effort 3 will be the most largest, the greatest, and the compactive effort 1 will be the smallest. And also, you can draw the line through this maximum dry density, and this is called the line of optimum. And below water content, the optimum water content, so in the region of the dry optimum, as the water content increases, water film develops and which acts as a lubricant. So this makes the particles to move easily into a denser state during the impact. So this is the conventional theory and the explanation people often to use. But recently, the water film explanation, instead of the water film explanation, people use the capillary force, because actually that as you have smaller water amount, the capillary force increases, so that binds the particles more. So this capillary force is more resulted by the presence of the water in the dry optimum. So that increases the dry density. And above the water content, optimum water content, which is the west side of the optimum, as the water content increases, water starts to replace the particles. So that increases the void ratio and decreases the dry density. And on the top of the compaction curve, we can also plot the another curve for the different degree of saturation for a specific soil. So remember that this relation, that the WGS is equal to the void ratio times degree of saturation. So from here we can manipulate the equation to be the void ratio E is a W times GS over S. And we also know that the dry density is rho S over 1 plus E. So from here we can derive this equation. And if we replace the void ratio with this equation, so we're just inserting here to remove the E, then we get this final equation. So in this equation, the dry density rho D is equal to GS times the rho W over 1 plus WGS over S. So from this relation, we now know that as the W, the water content increases, we can expect that degree of denseness or the dry density decreases, or if the degree of saturation increases, so the dry density increases. So if we plot it on the compaction curve here, let's say that this is the compaction curve, then we can plot the theoretical curve, the rho D versus W curve. So here we have one curve, another curve, and another curve. So I say that this is the S1 and S2 and S3. So as the degree of saturation increases, the dry density increases. So we can expect the S3 will be the largest and S2. After that, S1 is the smallest degree of saturation. say that this is the 100%. If the S3 is the 100%, then this will be around like 80%, and this is, for example, it's gonna be like 60%. And Eab curve corresponds to the curve with the degree of saturation of 100%. So this curve is called the Eab curve. And also the line of optimum, you know that as we increase the compactive effort, you will have a different curve like this, right? And this compactive effort, with different compactive effort, we will have a different compaction curve. And if we connect the optimum point to draw the line of optimum, then this line of optimum is almost like parallel to the Eab curve. So if I show you the representative or the typical result of the compaction, this will be the graph to refer to. So standard Proctor test, you have one curve, and from the modified Proctor test, you have another curve like this, right? And the optimal water content obtained from the standard Proctor test, W of T of the standard will be around here, and the optimal water content from the modified Proctor test will be around here. And typically the difference between this optimal water content from the standard Proctor test and the modified Proctor test are about 3 to 5%. And most soil, particularly cohesive soil, show a distinctive peak in dry density around the range of the 80% to 90% saturation. If you go back to the previous curve, this is around the degree of saturation in the range of 60 to 80%. So typically, if it's coarse grain soil, it's going to be around 70%. If it's fine grain soil, it's a little bit more than that, so 80 to 90%. And the rho D max, so the maximum dry density, is only achievable if the soil is at its optimal water content. So you have to have an optimal water content. You have to control the water content to be optimum to achieve, to obtain the maximum dry density. But for some soil, the concept of this single optimal water content may not be applicable. For example, the highly permeable granular soil may densify best if the completely if it's dry or completely saturated. So this is very rare case, but you can encounter some of these soils. And the other example is that when you have the organic soil, very organic rich soil like peat, then the dry density may just simply increase with the increasing water contents. And the other laboratory compaction test in the past people used is the minimum Harvard compaction test and the static compaction. The minimum Harvard compaction test is that they use the kneading to simulate the temper foot roller, but it's not normal recommended by the ASTM. Static compaction is that you apply the static force, steadily increasing the force like a consolidation. So the particle orientation may not change during this static loading because you're compressing the soil in a oedometric condition. It's suitable for the fine grain soil, but it's not simulating properly the coarse grain soil compaction.